Imagine that Earth is not a cold, indifferent rock, but a gigantic copper coil resting inside a cosmic generator. The principle is simple enough to write on the back of a notebook. When a strong magnet sweeps past a coil, an electric current is born. In the last 72 hours, that invisible current seems to have surged. Somewhere deep under our feet, the coil of Earth has started to hum. In Ethiopia, a volcano that has slept for roughly 10,000 years has opened its eyes. Cameras capture a dark ridge that once blended into the highland horizon, now glowing with orange veins. Almost in the same breath of planetary time, seismographs in Indonesia, Mexico, and Hawaii begin sketching the same restless pattern. To the spreadsheets of mainstream geology, this is a statistical cluster. To those who listen to patterns instead of averages, it feels like a pulse. Most official explanations are looking in one direction. They are looking toward the sun, counting solar flares and cataloging geomagnetic storms, searching for a familiar culprit. But in the star-washed dark beyond Mars, another suspect is moving far more quietly. New observations confirm that 3IA Atlas is not a fluffy snowball of ice and dust. It behaves like a vast metallic hull, rich in nickel and other conductive metals, racing through space at around 137,000 miles per hour as it moves toward a close approach around December 19th. Trailing behind 3I Atlas is a filament of ionized gas that stretches for millions of miles. It is not a soft cloud. It is closer to a plasma cable, a charged streamer that wraps around lines of magnetic force like a live wire draped across an invisible grid. As that enormous tail drifts closer to the region of space that Earth occupies, it has the power to do more than reflect sunlight. It can induce current. It can reach across the vacuum into the crust and speak directly to rock. In that picture, Earth is not sick. Earth is being driven. A foreign magnetic presence is gliding past the coil, drawing out currents that never existed in this exact way before. Those currents may be racing through quartz-rich crust, down subduction zones, into magma chambers that were content to sleep. What we read on the surface as a spike in eruptions might, in this frame, be nothing more than the glow of overloaded circuitry. Here on Dreamy Stargazer, our purpose is not to shout over breaking news, but to slow the frame rate of cosmic events until you can see the hidden motion between each image. We wander along the thin line where hard data ends and quiet speculation begins. Tonight, we will treat Earth as a living circuit, and 3I Atlas as a new current crossing that circuit, touching both sky and stone. If you find comfort in calm journeys through dark possibilities, you can gently anchor this channel in your own orbit. You can subscribe, leave a quiet like, or share this episode with someone who also watches the night. Tell us in the comments where on Earth you are listening from, and whether the ground where you live has felt different lately, even if only in your imagination. Now, dim the lights. The first file we open begins in the Ethiopian highlands, where the air is thin and the ground remembers ice ages. The volcano that has seized our attention rises like a broken tooth from a plateau of ancient lava. For generations, local villagers have treated it as part of the background. It was a mountain, not a question. The story of its last eruption lived only in myths about fire and ash that came before written memory. To a geologist, 10,000 years is longer than civilization, but shorter than the age of a continent. A volcano can sleep through the rise and fall of empires and still be considered temporarily quiet. Yet, even in that context, the silence over this Ethiopian vent was extraordinary. Radiocarbon traces in buried ash suggest its last major outburst near the end of the last ice age, when glaciers were retreating and sea levels were still hundreds of feet lower than today. Seismometers scattered across the region began to sense the change before any human eye. The background noise of the crust thickened into a low, steady vibration. Harmonic tremors, like the sustained note of a distant organ, started to appear in the data. At first, the signals were filed under routine tectonic adjustment. Only when sulfur began to leak from old fissures and small villages, reported animals refusing to graze, did the pattern gain a name. Beneath Ethiopia and much of East Africa lies a structure that geophysicists call a superplume. It is a deep, rising column of unusually hot mantle material, an upwelling that has been feeding volcanoes and stretching the continent apart for millions of years. On paper, it is mapped as colors on a tomography chart, a red smear beneath a gray continent. In the mind's eye, it looks more like a slow, luminous river pulsing upward from the core mantle boundary. This superplume is sometimes described as part of the planet's internal engine. It carries heat from deep within, delivering it to the thin crust, where we build our cities and write our histories. Where it touches the base of the lithosphere, the rock softens and swells. Over geological time, that softening creates rifts. The East African Rift is one such scar, a place where the continent is literally being pulled in two. Now imagine that this superplume is not only a thermal structure, but also an electrical one. The same minerals that allow it to carry heat also influence how it carries charge. Magnetotelluric surveys hint that parts of this rising column are more conductive than the surrounding mantle. In simple terms, it can serve as a path of least resistance for any large-scale electromagnetic stress imposed from above. If 3I Atlas is truly dragging a charged plasma tail through the magnetic environment of the inner solar system, then Earth's mantle and crust are not passive spectators. They are components in a circuit. A subtle change in external magnetic pressure could redistribute currents along deep conductive pathways, focusing energy into regions like the African superplume first, simply because the wiring there is already primed. From the outside, this hypothesis competes with more comfortable explanations. Many volcanologists will point to long-term cycles in magma supply or slow shifts in plate boundaries and stop there. Those stories are not wrong. They are simply incomplete if there is an additional, temporary driver acting from the sky. When you overlay the timeline of increased seismic restlessness in Ethiopia with the inbound trajectory of 3I Atlas, the two curves do not prove a connection, but they rhyme. Picture for a moment a night watchman stationed near the slopes of this awakening volcano. The stars above him wheel past as they always have. 3I Atlas is far too faint for his naked eyes, yet his phone flickers when he holds it near certain boulders. He hears a low, almost musical rumble under his boots that no one else on the radio seems to notice. Before lava ever breaks the surface, the world around him feels fractionally out of tune. Whether that feeling is psychological or physical is part of the mystery we are tracing. What matters for our story is that Earth itself is registering something. One dormant vent in Ethiopia has joined a growing chorus of unrest. In the next part, we will step back from this single mountain and listen to the entire ring of fire to see whether this supposed pulse is local noise or the first beat of a global rhythm. When we step back from the lonely volcano in Ethiopia and let the map widen, a new pattern begins to glow. The continents curve around the Pacific basin like the rim of a great drum. Along that rim runs a chain of volcanoes and trenches that textbooks simply call the Ring of Fire. Over the last 2 days, that ring has behaved less like a line on a diagram and more like an instrument being played. In Indonesia, Semeru has thrown ash into the upper air again, its plume rising above a landscape that already knows the taste of volcanic dust. The cameras show a gray column that blooms, then shears sideways under the wind, lightning flickering inside for a brief electric heartbeat. Far across the ocean, Popocatépetl near Mexico City sends its own dark breath into the sky, a steady exhale of ash and gas that stains sunrise and sunset. On the island of Hawaii, the restless shield volcano Kilauea begins what local scientists quietly call its 37th eruptive episode in recent years, as if the planet were clearing its throat in 3 different languages at once. On paper, each of these eruptions has its own local cause. Magma rose along a conduit here, gas pressure built inside a chamber there. A small intrusion of fresh melt occurred under an old lava lake. Yet when seismologists lay the timelines of these events side by side, the start times begin to crowd together inside a window of roughly 48 hours. Individually, each ignition is explainable. Collectively, they look like notes in a chord. Statistical models do allow for clusters. In a world with hundreds of active volcanoes, some will flare up close together in time simply by chance. That explanation is safe, and it is often correct. But the more we learn about how Earth's plates, mantle, and magnetic environment are intertwined, the less satisfying it becomes to treat every coincidence as meaningless. Somewhere between pure randomness and rigid causality lies the idea of a systemic event, where many parts of a complex system respond to the same subtle nudge. The Ring of Fire itself is already a system. It traces the edges of tectonic plates that dive beneath one another, stacking oceanic crust into deep trenches and feeding magma upward toward chains of islands and mountain ranges. Subduction zones recycle the seafloor into the mantle, release water into hot rock, and prime volcanoes for eruption. The ring is where the planet breathes out its internal heat. When several segments of that ring twitch together, it is reasonable to ask whether the same unseen hand brushed against them all. In the control rooms of observatories, this twitch is written in lines of ink or strings of numbers. Broadband seismometers record similar harmonic tremors before eruptions at Semeru and Kilauea, patterns that look like long, wavering tones instead of sharp jolts. Infrasound arrays in Mexico pick up low rumbles that match the rhythm of Popocatépetl bursts. When researchers overlay these patterns with the growing catalog of geomagnetic disturbances recorded over the same period, an odd alignment appears. Mild but global magnetic fluctuations crest and fade just before the most vigorous volcanic pulses. This is where 3I Atlas quietly enters the frame again. While human attention is fixed on the ash columns and lava fountains, the interstellar visitor is cutting through the solar system's magnetic field like a moving blade of metal. Its conductive hull and long plasma tail interact with the heliospheric current sheet, that thin, warped surface where the sun's magnetic polarity changes sign. As 3i Atlas crosses those invisible boundaries, it stirs currents that radiate outward along magnetic field lines, not just toward the sun, but also toward the planets that sit downstream. If Earth is part of that downstream circuit, then the Ring of Fire is one of the places where incoming electrical stress may find it easiest to ground itself. The subducting slabs beneath the Pacific are hydrated and fractured, threaded with minerals that can carry charge more easily than cold, dry rock. Conductivity maps show channels where electromagnetic energy can flow along plate boundaries for hundreds of miles. In such a model, an external pulse arriving from space would not simply wash over the planet. It would seek pathways, concentrate, and ring along the edges of the plates like a finger tracing the rim of a crystal bowl. Imagine the Ring of Fire as a nearly continuous loop antenna encircling the Pacific. The crust and upper mantle form the wire, the ocean is the dielectric medium, and the slowly changing geomagnetic field is the background hum. Now imagine the plasma tail of 3i Atlas brushing through the broader magnetic environment, introducing a small but coherent variation, the way a musician might pluck a single string in a darkened room. The induced currents would not be huge, but they would not need to be. In systems already close to critical pressure, even a slight additional stress could tip magma from stable to mobile, gas bubbles from compressed to expansive. For the people who live on the flanks of these volcanoes, the language of induction coils and antennas feels distant. Their reality is simpler and more immediate. In Indonesia, fine ash begins to settle on crops and rooftops, making every surface slick when it rains. In Mexico, residents capture videos of halos and strange glows around Popocatépetl at night, arguing in comment sections about whether the colors are camera artifacts or signs from the sky. On Hawaii's Big Island, tourists gather at safe viewpoints to watch lava pour into craters, unaware that the mountain they are filming is being discussed in research papers as part of a global acceleration. Official bulletins stay calm. Agencies describe the activity as elevated but with unexpected patterns for these historically active volcanoes. They use phrases like statistical coincidence and natural variability. These words are not lies, yet they focus the story inward on each volcano's personal history and step carefully around the growing suspicion that something has changed in the way the planet as a whole distributes its stress. If you read between the lines of internal reports and conference talks, you sometimes find a different tone. A researcher might note that harmonic tremor signatures at distant volcanoes have become unusually similar, as if driven by a shared modulation. Another might point out that the timing of certain eruptive surges correlates more strongly with short-lived geomagnetic anomalies than with measured changes in local tectonic strain. None of this is enough to claim a cause, but it is enough to ask a harder question. What if the Ring of Fire is reacting not only to forces from the mantle, but also to a pattern whispered in from space? The thought is unsettling because it makes the ground feel less isolated, less self-contained. It suggests that when we walk along a beach in Hawaii, or across a cornfield in Mexico, or through a village in Java, we are standing on parts of a single, connected circuit. Each tremor and eruption is not just a local event, but also a response, however faint, to a change in the larger cosmic environment. If 3i Atlas is tugging on that environment with its metallic mass and luminous tail, then every new surge along the Ring of Fire could be read as a syllable in a conversation that began far beyond our sky. What might that conversation be about? Is Earth simply ringing in sympathy with a passing magnetic disturbance, the way a glass sings when a train goes by, or is there something more adaptive taking place? Could the pattern of eruptions, the so-called orchestration of the Ring of Fire, be part of a deeper attempt by the planet to rebalance itself under a new kind of stress? These are not answers, only questions, but they are questions that grow louder with each overlapping eruption. For now, we can only listen. We listen to the ash falling, to the tremor lines on graphs, to the quiet shift in how often alerts appear in our feeds. We note the way different volcanoes on opposite sides of the ocean seem to wake and breathe in near unison, then fall back into uneasy rest. We understand that statistics can account for many of these overlaps, but we allow ourselves to wonder whether statistics are sometimes the language we use to comfort ourselves when a system moves in ways we do not yet understand. In the next part of our journey, we will turn away from the noisy edges of continents and look into the deep ocean basins where there are no cities, no news crews, and almost no direct witnesses. There, on the silent seafloor, lie other volcanoes, other faults, other instruments in the planetary orchestra. The reports from the abyss do not speak of eruptions. They speak of low, continuous vibrations and animals fleeing toward the coasts, as if something vast were growling just below the threshold of human hearing. If the Ring of Fire is an instrument being struck, then the deep ocean is the room it is playing in. Above sea level, we have endless footage of ash and lava. Below the waves, there are no cameras, no tourists, only sensors and animals listening in the dark. The strangest part of the last few weeks is not what we see on land, but what we barely hear under thousands of meters of water. Across the Pacific and into the Indian Ocean, networks of hydrophones originally deployed to track submarines and undersea landslides have begun to report a peculiar pattern. Instead of sharp, local booms that betray a nearby eruption, many stations are registering broad, low-frequency hums that rise and fall together over vast distances. To human ears, compressed and played back through speakers, they sound like the slow breathing of some enormous, unseen machine. On paper, these hums are classified as infrasound. Their dominant frequencies sit far below the range of human hearing, down in the territory where vibrations are felt more in the body than heard in the air. Marine biologists have long known that whales and other large sea creatures communicate and navigate partly through such deep tones. In the last month, recordings show those natural calls overlapped by a persistent, planet-scale murmur that does not match any familiar cataloged source. If the seafloor were erupting violently all along the mid-ocean ridges, the story would be simple. We would expect heat anomalies, rising plumes, new volcanic cones mapped by sonar. Instead, oceanographers are seeing something closer to the opposite. The usual small, scattered signs of ridge eruptions have gone oddly quiet, as if the usual simmer of submarine volcanoes had been turned down just as the continental arcs flared. The crust under the ocean is not exploding, it is humming, yet the creatures that live in that humming world are not calm. Reports from multiple coasts describe stranded whales and confused pods of dolphins washing up on beaches in numbers that local rescuers call unusual but not yet catastrophic. In some regions, ship captains speak of vast, empty zones where they once saw regular surfacings. It is as if entire populations have shifted their paths inland, away from unseen corridors of sound or pressure. Official explanations point, as they often do, to sonar tests, toxins, plastic pollution, and changing currents. All of these are real stressors, none of them are new. What is new is the timing, the way these marine displacements cluster around the same windows when the ring of fire intensifies and the geomagnetic indices quietly jump, then settle, then jump again. When you overlay the charts, the land, the sea, and the sky begin to move in something like rhythm. From the perspective of an electrical planet, the oceans are not just water. They are conductive blankets draped over basaltic crust, saline layers that help close circuits between different parts of the globe. Salty seawater carries charge far better than dry rock or air. If 3i Atlas is indeed dragging a changing magnetic field through the inner solar system, the oceans may be the first and broadest surfaces on Earth to feel its passage as distributed, induced currents. Imagine a sheet of slightly conductive gel wrapped around a metal core. Pass a magnet near it, and faint currents swirl through the gel long before any spark leaps from its surface. In our case, the gel is the world ocean, and the magnet is the metallic hull and plasma tail of 3i Atlas, modifying the magnetic environment at large. Those induced currents might be too weak to trigger dramatic eruptions on the seafloor, but strong enough to alter how pressure waves and sound propagate through the water column. A small, coherent change in the electrical properties of seawater could subtly bend low-frequency sound paths, distort the way infrasound carries, or shift the zones where marine animals are comfortable hearing and calling to one another. To us, such a shift would be almost invisible, hidden in the data of hydrophones and signal processing logs. To a whale, whose entire social world is built on distant, low notes, it could feel like a sudden fog rolling into its only language. Another possibility is simpler and stranger. The infrasound hum itself, that global, slow vibration recorded across distant ocean basins, might be the voice not of local geology, but of the whole Earth shell responding to an external push. Just as a bell rings in a characteristic tone when struck, the combined lithosphere and hydrosphere have natural frequencies of oscillation. A passing electromagnetic disturbance tied to 3i Atlas could be exciting one of those modes, making the planet ring softly in a register we rarely monitor. In such a scenario, the silence of submarine eruptions is not a contradiction. It is a clue. The energy that might have emerged as scattered volcanoes along the mid-ocean ridges could instead be trapped as stored stress and vibrational motion, redistributed into the continental margins where the crust is thicker, more brittle, and already segmented by faults. The oceans absorb the hum and pass the focused strain to the edges of the plates, where Ethiopia, Indonesia, Mexico, and Hawaii feel it as fire and quake. There is a psychological dimension to this silence as well. Land eruptions frighten us, but they are visible. Cameras can watch them, pilots can fly around their plumes, satellites can photograph their ash clouds. The ocean's response, by contrast, remains mostly invisible, translated for us only through graphs of pressure waves and scattered reports of beach strandings. It is easier, in a way, to accept a bright lava fountain than to accept that the entire ocean might be shivering in tune with a visitor we can barely see. If Earth is a circuit, then the seas are not empty gaps between continents. They are the fluid parts of the wiring, the places where currents loop and close and return. When a foreign magnetic presence like 3i Atlas enters that circuit, The response will not be neatly contained to one volcano, one island chain, or one city. It will appear as a pattern, a distributed unease, with some pieces visible and others hidden in the deep. For now, the hum continues. Hydrophones write their slow, undulating lines. Whales alter their routes in ways we are only beginning to track. Along the coasts, people hear about eruptions on the evening news and fall asleep to the familiar wash of waves, unaware that the water itself is carrying an unspoken tension. Somewhere beneath every harbor and bay, the crust vibrates at frequencies no one has taught us to fear. In the next section of our journey, we will move from symptoms to mechanism. We will leave coasts and currents and step into the physics of stone and charge, asking whether 3I Atlas and a network of quartz-rich crust could truly share the same unseen planetary switch. Before we can talk about how a planet might be electrically stressed, we need to return to something small enough to hold in one hand. Think of a quartz wristwatch quietly ticking on a bedside table. Inside it, a tiny crystal flexes at a precise rate when voltage is applied, keeping time by turning electricity into motion. The same principle hides in gas lighters, where a sharp press produces a spark, and in the pressure sensors that watch over bridges and aircraft. This is the piezoelectric effect, the talent of certain crystals to turn force into electricity and electricity back into force. In the classic version of the effect, you squeeze the crystal and get a tiny pulse of voltage. Press hard, and the charge rises. This is the story taught in basic physics and engineering classes. The less familiar story reads in the other direction. If a crystal can turn mechanical stress into electric potential, then feeding current back into the same structure can make it stretch, twist, and vibrate. Laboratory experiments confirm this reverse mode. Apply a voltage across a quartz sliver, and its lattice shifts by microscopic amounts, enough to move a watch hand or steer an ultrasonic beam. Now remove the crystal from the laboratory bench and imagine it writ large. Continental crust is not pure quartz, but many of the rocks beneath our feet, especially granite, are laced with quartz-rich veins and grains. Over wide areas, these minerals form networks that are mechanically connected and electrically sensitive. In a sense, each mountain range carries within it a diluted, tangled version of the same piezoelectric behavior that keeps a watch on time. When stress builds up along a fault, those grains are squeezed. It is no coincidence that some earthquake zones release faint, transient electric anomalies just before a rupture. In the reverse picture, the direction of cause and effect changes. Instead of tectonic stress-generating charge, an incoming electric current could nudge the lattice first, subtly altering stress conditions in the rock. If a coherent current were to flow through a quartz-rich segment of the crust, it would not simply heat the rock. It would also cause micro-expansions and contractions, nanoscale breathing motions that add or subtract from the larger tectonic forces already present. Over many square miles, that nanoscale behavior could influence how and where fractures open. We already know that space can drive electricity into the ground. During strong geomagnetic storms, long power lines have acted like antennas, collecting induced currents that overload transformers and darken cities. In one famous storm near the end of the 20th century, an entire regional grid collapsed when extra current poured through its infrastructure. Those events are well documented and generally framed as threats to technology, not to rock. Yet the same induced currents that trouble our power systems do not stop at the last transformer. They continue to seek paths of least resistance through soil, sediment, and fractured stone. If the magnetic environment around Earth is changing in a new way because of 3I Atlas, then the pattern of these induced currents could also be changing. The metallic hull and plasma tail of 3I Atlas may be rearranging the geometry of the heliospheric magnetic field on certain scales, altering where and when the planet experiences subtle surges of electric stress. These would not arrive as dramatic lightning bolts, but as broad, slowly varying currents that seep into the crust over regions that are already strained and heterogeneous. Now imagine one of those regions under a restless volcano. Beneath the surface, the rock is a patchwork of solid blocks, old faults, fluid-filled fractures, and rising magma. Quartz grains and veins are woven through this patchwork like threads. A small increase in current density, guided by the rock's own conductivity pattern, might focus along a few key pathways. Where the charge concentrates, the reverse piezoelectric effect goes quietly to work, flexing the crystal lattice in countless tiny motions. Each motion is too small to feel, but together they can tip the balance in places where magma is poised at the edge of motion. There is empirical smoke around this idea. Before some large earthquakes, observers have reported strange lights flickering in the sky, luminous bands near the horizon, or glows dancing along fault lines. Measurements have sometimes captured spikes in local electric field strength, bursts of low-frequency electromagnetic noise, and odd behavior in underground water chemistry. Not every report survives careful scrutiny, but the pattern is persistent enough that some researchers treat pre-seismic electrical and optical anomalies as a real, if poorly understood, part of crustal physics. In a world where Earth is a closed system, such anomalies might be driven entirely by internal stress redistribution. Cracks form, fluids move, charges separate, and the crust lights its own warning candles. In the extended picture, 3I Atlas could be acting as an external drummer, setting the beat to which these processes synchronize. The foreign magnetic presence modifies the background field, induced currents rise ever so slightly, and the crust's natural tendency to produce electric precursors is amplified. A local system, pushed just a little closer to its tipping point, responds in kind. This is where the reverse piezoelectric effect becomes more than a physics curiosity. It offers a mechanical route for those induced currents to change not only our power grids, but also the stress landscape inside volcanoes and along faults. The rock is no longer just a passive resistor, it becomes an active transducer, turning current into strain. In that frame, a spike in geomagnetically induced current during a period of strong 3I Atlas interaction might be able to advance the clock on an eruption that was already due, pulling future events into the present and clustering them in time. There is a quieter, more unsettling layer beneath this. For decades, militaries and research agencies have studied the interaction between electromagnetic fields and rock, officially in the context of communications and resource exploration. Declassified fragments hint at experiments where intense radio frequency or low frequency fields were used to probe faults and even to see whether small changes in stress could be induced at depth. Publicly, no one claims to command earthquakes or volcanoes. Privately, the fact that such experiments were pursued at all suggests that the idea of an electrically sensitive crust is not pure fantasy. If a handful of antennas on Earth can, in principle, influence stress fields on small scales, what happens when an object the size of 3I Atlas, with a conductive hull and a 5 million kilometer plasma tail, drifts through the electromagnetic environment that bathes our planet? We are no longer talking about tightly focused beams, but about grand, slow modulations of magnetic flux and induced current that seep into every conductive channel available, from power lines to subduction zones to quartz-rich batholiths beneath old volcanoes. Picture the crust beneath a volcanic arc as a vast, three-dimensional lattice of piezoelectric fragments, each one capable of flexing slightly when current passes through. Under normal solar conditions, random fluctuations tug at this lattice, adding a faint buzz to the tectonic hum. Under the influence of 3I Atlas, the pattern of tugging may become more organized, more persistent, or more intense, enough to raise the background state of mechanical agitation by a fraction. That fraction, unfortunately, is all it takes in places where magma is already buoyant, gas-rich, and confined. From the surface, we do not see the crystals flex. We see fumaroles grow hotter by a few degrees, gas emissions shift their ratio, and small earthquakes begin to cluster. Monitoring stations report these changes one by one, each with its own local explanation. It is only when someone dares to plot them against the timeline of external electromagnetic disturbances against the evolving position and activity of 3I Atlas that an uncomfortable resonance begins to emerge. If we had a true global map of electric current flowing through the crust in real time, a living X-ray of the planet's wiring, what would it show us this month? Would we see bright, branching paths connecting the African superplume to the Ring of Fire, and those in turn to regions beneath Mexico and Hawaii? Would those paths flicker and thicken in rough synchrony with subtle inbound changes in the magnetic field traced back to the track of 3I Atlas? Or would the map reveal something even stranger, a pattern of currents that form a shape we do not yet have the language to describe? For now, we are left with indirect evidence and an uneasy fit between what traditional geology predicts and what we are actually measuring. The reverse piezoelectric effect, once a textbook footnote, becomes a bridge between hard science and speculation, a mechanism that allows a visitor in space to leave fingerprints in stone. In the next chapter, we will examine 3I Atlas itself as part of a planetary scale induction coil, asking how its motion through the solar magnetic field might be generating the very currents that set this hidden mechanism in motion. In every power plant, there is a forgotten room where the real magic happens. A heavy rotor spins inside coils of copper, cutting through magnetic fields and forcing electrons to move. Spinning metal, wrapped in magnetism, becomes current. The equations that describe this process fit on a single classroom board, yet they keep entire cities lit. What happens if we take that same principle and stretch it until the rotor is an interstellar object and the coils are the invisible tendrils of the sun? Far from looking like a neat bar magnet, the sun's magnetic field curls outward in a spiraling pattern carried by the solar wind. As charged particles stream away, they drag field lines with them, twisting the heliosphere into something that looks, in simulation, like a slowly turning whirlpool of magnetism. Every planet or comet that orbits inside this structure spends its life drifting through these twisted lines, quietly cutting across them as it goes. Most comets are poor conductors. They are dirty snowballs, loose mixes of ice and rock that can hold a charge only in thin surface layers. Their interaction with the field is modest, a kind of ghostly drag. 3I Atlas, if the latest readings are correct, is not modest. It appears to be wrapped in a shell rich in nickel and other metals, a hull rather than a snowball, giving it a conductivity far closer to that of an engineered object than a fragile conglomerate of dust. As 3I Atlas races through the inner solar system at tens of miles per second, its metallic body does exactly what the rotor in a generator does. It slices across magnetic field lines. According to Faraday's law, that motion through the field induces a voltage along the object. Where there is voltage, there can be current. But instead of copper wires neatly wrapped around it, 3I Atlas carries a tail of ionized gas millions of miles long, a plasma filament ready to accept and conduct whatever current the motion demands. Picture that tail as a flexible, luminous cable trailing behind a high-speed train. The surrounding magnetic field acts like a vast transformer core. As the conductor cuts through the field, current is driven along the tail, which in turn modifies the local magnetic environment. The system does not simply move through the heliosphere. It pushes back, carving its own temporary pattern into the magnetized wind, leaving behind an electrically charged wake. In this frame, 3I Atlas is not just a visitor. It is the primary winding of a wandering, cosmic-scale induction system. Its hull and tail form a moving circuit that pumps energy into the surrounding plasma. That energy can couple into nearby field lines, propagating outward as subtle disturbances that ride the solar wind like ripples. These ripples do not respect our idea of borders. They travel along magnetic connections that may link the visitor, the sun, and the planets in ways that are not obvious on a flat map. Earth occupies one node in that larger web. Our planet is wrapped in its own magnetic bubble, the magnetosphere, which is itself threaded with currents along lines that connect back to the solar wind. In auroral ovals near the poles, streams of charged particles pour down along these lines, igniting curtains of light. Higher up, long, thin structures, known as flux ropes or current sheets, form where the solar wind's magnetic field locks temporarily onto Earth's field. In those regions, the boundary between our local space and the wider heliosphere is not a wall. It is a handshake. Now add 3I Atlas to this handshake. As the visitor's induced currents distort nearby field lines, some of those distortions will ride outward until they intersect the lines that thread into Earth's magnetosphere. The result is a kind of magnetic whisper, a slow, deep modulation superimposed on the usual noise of solar variability. It will not look like a normal solar storm, with sharp spikes and sweeping arcs on charts. It will look like a broad, rolling wave, easy to overlook, unless you are watching for patterns that repeat when 3I Atlas occupies certain longitudes. On the days when those waves reach us, Earth's magnetosphere behaves a little differently. Flux ropes form in slightly new places. Auroral activity becomes more restless without a clear solar flare to blame. Geomagnetically induced currents rise just enough to trouble the longest power lines, to confuse some pipelines, and to nudge the background electric stress in the crust. To a casual observer, all of this disappears into the category of space weather. To someone tracing the orbit of 3I Atlas, it looks more like the secondary coil of a transformer being brushed again and again by the same moving field. Behind closed doors, small teams in space weather centers may already be wondering about this. Their internal plots show a soft resonance between the passage of 3I Atlas through key sectors of the heliospheric current sheet and unusual patterns of disturbance at Earth and Mars. Officially, they attribute the changes to normal variability in the solar wind. Quietly, they test models where a conductive interstellar object adds a term to the equations, a term that behaves more like a generator rotor than a piece of drifting debris. If that term is real, the consequences reach far below the magnetosphere. When magnetic fields threading through Earth's environment change even slightly, they induce currents in any conducting loop they can find. Our planetary crust, with all its faults, ore bodies, and fluid-filled fractures, is one such loop. Oceans and ionosphere form others. Together, they make Earth part of a planetary scale induction coil, one that can be driven not only by the sun, but by any large conductor that wanders through the shared magnetic medium. There is an eerie elegance to this picture. You can think of 3I Atlas as a traveling turbine in a river of magnetized plasma, with its tail as the shaft and its hull as the blades. As it turns, it alters the flow, which in turn induces currents in any nearby object embedded in the same river. Planets, moons, and even smaller bodies all feel a version of this interaction, proportionate to their own conductivity and position. Most of them have no observers, no instruments, no names for the stress they endure. Only on Earth do sensors and stories multiply fast enough to notice that the ground has started to respond. For a moment, allow an imaginative leap. Suppose 3I Atlas is not just an accidental generator, but a deliberately hardened, conductive shell designed to maximize its interaction with magnetic fields. In that case, it is not only a traveler, it is also a probe or a tool capable of harvesting a small fraction of the energy stored in stellar magnetic structures as it passes. Each system it visits becomes, briefly, part of its power supply or its sensor array. Under that hypothesis, Earth is not merely collateral. It is a component in someone else's circuit. Even without that darker reading, the induction coil model is troubling enough. If an object like 3I Atlas can use the sun's own magnetism to pump extra current into our environment, then our catalog of natural hazards is missing a category. We plan for solar flares and coronal mass ejections. We do not plan for interstellar hulls that act as temporary generator rotors, turning the entire inner solar system into a machine that has never run in this configuration before. How many of the volcanic spikes and synchronized tremors we are now recording would have occurred anyway, in a quiet solar year with no interstellar visitor? No one can say with certainty. Yet the timing of the most intense pulses, the way they align with particular sectors of 3I Atlas's path through the heliospheric current sheet, invites a question that mainstream reports rarely write down. Are we living through a random uptick in tectonic coincidence, or are we watching a transformer slowly wind up as a foreign conductor pushes deeper into the sun's field? In the next part of our investigation, we will narrow the focus from broad, slow currents to something far more specific and unsettling. Among the wide spectrum of frequencies that bathe our planet, one band around 2.4 gigahertz has flickered in a way that some consider a mere instrument glitch, and others quietly suspect might be the precise key used to unlock certain resonances inside the Earth's own electrically sensitive shell. Some events announce themselves with ash clouds and earthquakes. Others hide in the static. What happened on November 19th did not ring church bells or crack highways. It started as a whisper inside machines. Across a patchwork of observatories and communication networks, technicians later found the same odd bruise on their logs. For a narrow slice of time, just a few minutes long, receivers that normally monitor wide ranges of radio noise showed a sudden, sharp swell centered near 2.4 gigahertz. The spike did not saturate the instruments. It brushed them like a finger on piano keys, then faded back into the usual background. On the surface, 2.4 gigahertz is an ordinary number. It is the frequency band used by home Wi-Fi routers, cordless phones, baby monitors, and countless other devices that fill our cities with invisible chatter. Engineers chose it partly because it sits in an unlicensed region of the spectrum, and partly because it couples reasonably well to water molecules, the same reason household microwave ovens operate around 2.45 gigahertz. In our kitchens, that band is used to boil water in a mug. In the upper atmosphere, it is just another part of the radio sky. What made the November 19th disturbance stand out was not its raw strength, but its reach. The anomaly appeared not only in ground stations, but also in data from weather satellites and deep space dishes that were, by chance, looking near the inbound track of 3I Atlas. In several cases, the spike was first flagged as interference and removed automatically by cleaning algorithms. Only when a handful of analysts compared notes did they realize that many systems had scrubbed the same fingerprint. Official reports, where they exist at all, speak in cautious phrases. Instrument crosstalk, reflections from terrestrial sources, an unfortunate overlap with a surge in consumer device usage. It is easy to blame a frequency that our own technology uses so heavily on ourselves. Yet when the timestamps are compared to seismic records, a troubling pattern begins to form. Within hours of the 2.4 gigahertz swell, a distinct uptick in volcanic tremor appears along segments of the Ring of Fire and beneath the restless Ethiopian plume. The conservative view is that the timing is meaningless. Correlation without causation. After all, magma chambers do not carry Wi-Fi passwords. They do not listen to baby monitors. The rocks beneath our feet should be deaf to this band of the spectrum. The more unsettling view starts with a simple question. If 2.4 gigahertz can agitate water in a cup, what might it do to a world whose crust and mantle contain vast volumes of conductive fluids and superheated, partially molten rock? Domestic microwave ovens focus energy inside a metal cavity, using standing waves to jiggle water molecules until friction turns to heat. The Earth is not a sealed box, and the November 19th event was nowhere near as intense. But the physics of coupling does not vanish simply because the scale changes. In certain conditions, a weak but coherent signal can have outsized effects if it resonates with natural modes of oscillation in a medium. The key is not brute force, but the matching of rhythm. Beneath volcanoes, magma is not a uniform liquid. It is a mixture of molten rock, crystals, and gas bubbles, threaded by conduits and pockets. As it rises, gas pressure builds. Small changes in temperature, even fractions of a degree, can change how easily crystals move, how bubbles merge, and how quickly channels open. If an electromagnetic field at a specific frequency couples more readily to certain ion-rich phases or to saline fluids in surrounding rock, it could add a tiny rhythmic push to systems already at the edge of instability. Here is where 3I Atlas returns to the center of the file. The metallic hull and plasma tail of 3I Atlas can, in principle, act as both antenna and transmitter. As it cuts through the sun's magnetic field, currents induced along its length do not have to remain smooth and broadband. They can break into oscillations, ringing at natural frequencies set by the geometry of the object, the properties of its plasma sheath, and its interaction with the heliospheric environment. One of those favored tones might sit near 2.4 gigahertz, not by coincidence, but by design or by the simple tuning of physics. Somewhere in a restricted annex of a research facility, there are likely plots that never made it into public releases. In those plots, the November 19th pulse appears as a narrow, clean peak near 2.4 gigahertz, aligned with the apparent position of 3I Atlas within the uncertainties of pointing and timing. Internal comments might note that the signal lacked the usual signatures of human transmitters. No modulation patterns, no spread spectrum encoding, only a pure, brief tone. The kind of tone you would send if your primary goal were not to carry information, but to test how a system rings. Imagine that test extended from space into the Earth itself. The pulse sweeps past, interacts with the ionosphere, and drives faint currents down along the existing paths carved by the induction effects we have already traced. Where those currents reach magma-rich regions, they add a microscopic, periodic push, a gentle stirring that either nudges gas bubbles upward or weakens the bonds holding crystal frameworks together. No one feels this on the surface. No thermometer records a dramatic jump. Yet at depth, thresholds shift. Processes that would have unfolded over weeks accelerate into days. From a monitoring perspective, the result is deeply ambiguous. Seismic instruments record an increase in small quakes and tremors. Gas sensors note that emissions have changed their ratios. Satellites observing thermal anomalies see subtle brightening in calderas that were already labeled as restless. To a volcanologist focused on local measurements, this looks like a natural escalation. To someone holding both the volcanic data and the radio logs, it looks like a planet that flinched right after a specific external knock. There is a more speculative strand that some investigators will not write down, except in notes that never leave their desks. They wonder about the strange symmetry in our choice of 2.4 gigahertz for household technology and the appearance of a similar band in an event apparently linked to 3I Atlas. Was our adoption of that frequency purely practical, or have we, without realizing it, tuned our technological environment into a band that is already favored by larger processes? If an interstellar object wanted to interact with a civilization and its planet at once, would it not choose a tone we have seeded into our own homes? In that imaginative leap, the November 19th pulse becomes a kind of combined handshake and probe. It excites resonances in our radio devices, causing brief glitches that engineers attribute to interference. At the same time, it propagates into the crust and mantle along conductive channels, mapping the response of magma chambers and fault networks to a specific spectral key. The signal is not a message in the human sense. It is more like a tap on the side of an aquarium, sent to see how the water moves. What matters for our story is not whether this reading is correct, but that the figures allow it. We have a documented narrowband anomaly at a frequency known to interact with matter in special ways. We have a coincident uptick in volcanic unrest and a known conductive interstellar object passing through the region of space from which the signal appears to originate. Mainstream narratives keep these facts in separate folders. The declassified file we are following places them side by side, letting the viewer decide whether the resulting picture is pattern or paranoia. If November 19th was a first key, a small, sharp knock at 2.4 gigahertz, then December 19th may represent something different. Not a single tone, but a sustained presence, as 3I Atlas reaches its closest approach and its induction effects on the solar and terrestrial magnetic fields peak. The pulse would then give way to a long, low power hum, the kind of input that does not test the system briefly, but drives it continuously. In the next section, we will shift our gaze to the largest intermediary in this process, the Sun. We will ask whether recent surges in solar flares and high-energy emissions are simply the Sun's own cycles playing out, or whether our star is acting as an amplifier, receiving the touch of 3I Atlas and passing it on to Earth in the form of light, particles, and perhaps a new season of volcanic fire. There are nights when the sky does not look like a ceiling at all, but like a fragile lens between us and something that is staring in. In those nights, every plume of volcanic ash, every thin veil of haze, begins to feel less like a nuisance and more like a curtain being drawn across a bright window. The question that opens this file is simple. What if Earth is quietly dimming the lights? History gives us a few rehearsal scenes. In 1815, the eruption of Tambora in Indonesia lofted so much ash and sulfur into the stratosphere that the following year was remembered as the year without a summer in parts of Europe and North America. Crops failed, frosts arrived in June, and sunsets turned blood red. In 1991, Mount Pinatubo in the Philippines injected millions of tons of sulfur dioxide into high-altitude winds, cooling global temperatures by roughly half a degree Celsius for several years. These events were local in origin, but global in effect. One volcano, in one country, altered the color of sunsets on the other side of the world and changed planting seasons for people who had never heard its name. Climate models that include these eruptions show clear dips in global temperature, slight but unmistakable, like a planet taking a shallower breath. That is the essence of a volcanic winter, not a frozen apocalypse, but a subtle dimming of the sun's warmth. Now imagine not one eruption, but many. Ethiopia's newly awakened giant, Semeru, Popocatépetl, Kilauea, and other restless cones around the ring of fire, all sending ash and sulfur upward within months of each other. Each plume on its own might be modest, manageable, a local hazard. Together, their particles could begin to accumulate in the stratosphere, layer upon layer, until the blue of the sky turns slightly milkier and the edge of the sun looks less sharp at noon. Volcanologists usually treat such alignments as bad luck, a rough year, but nothing more. Yet if Earth is, in some sense, an electrically sensitive body reacting to the presence of 3I Atlas, another interpretation opens. In that view, the volcanic winter scenario is not random overflow. It is the planet's equivalent of closing its eyes when a bright, unfamiliar light winds too close. The eruptions become both pressure valves and paintbrushes, spreading a thin shield of aerosols between the surface and whatever approaches. The physics of the shield is well understood. Sulfur dioxide injected into the stratosphere reacts to form sulfate aerosols, tiny droplets that scatter sunlight back into space. They do not care who lives below. They simply intercept photons and change their paths. The more of these particles gather at heights above weather systems, the less direct solar radiation reaches the ground. Temperatures dip, weather patterns shift, and the balance of energy in the atmosphere tilts toward cool. In the speculative file we are opening tonight, those aerosols serve a second purpose. If 3I Atlas is approaching with a strong magnetic signature and a luminous plasma tail, then the shape and intensity of the light reflected from Earth and of the radio noise leaking from our civilization are parts of the information it can gather. A denser, more reflective upper atmosphere would not only cool the planet, it would also blur the fine details in that outgoing signal. Here the hypothesis becomes more than climate science. It steps into a darker Gaia, the idea that Earth behaves like an organism that can respond to threats. In its gentler form, Gaia theory suggests that life and geology co-evolve to keep conditions habitable. Our scenario asks whether the same system could, under electrical stress from 3I Atlas, favor eruptions that cloak it, not to comfort life, but to reduce its visibility to a possible intruder. The shield is then not only about temperature, but about camouflage. We can look for hints of such a shield in data that are already being collected. Satellite instruments measure aerosol optical depth, a number that tells us how hazy the atmosphere is on a global scale. In ordinary years, these values rise modestly after major eruptions and then decay as particles settle or wash out. If the current cluster of volcanic activity is more than coincidence, we might expect a slower, more sustained rise, a lingering haze that does not match the output of any single volcano alone. At the same time, ground-based telescopes might begin to report a slight softening of starlight, a barely perceptible increase in atmospheric scattering, even on nights without obvious dust or cloud. Radio astronomers could see small changes in how the ionosphere reflects or absorbs signals, complicating their calibrations. None of these effects would scream of danger. They would feel like a planet adjusting its posture, changing the angle at which it shows its face to the sky. For the people living under these changes, the experience would be both subtle and intimate. Sunsets would become more dramatic, with deeper oranges and extended twilight. Summer afternoons might feel a little less sharp, temperatures a little more forgiving in some regions, harsher in others, as circulation patterns shift. Crops in marginal climates would respond, for better or worse. Animals that rely on light cues to migrate or breed might begin to fumble their timing. All of this could be described officially as a complex but natural interplay between volcanism and climate variability. In the HN file we are reading, however, there is an additional footnote. If 3I Atlas is indeed driving some of the volcanic spikes through electromagnetic induction and the reverse piezoelectric effect, then the shield is not entirely self-initiated. It is a feedback loop. The visitor stirs the crust responds with eruptions, the eruptions throw up a veil that changes how the visitor perceives the planet that is responding. Each new plume becomes both a symptom and a slight adjustment to the terms of contact. We can extend the imaginative leap further. Suppose 3I Atlas is not simply a passive sensor, but an active system that uses reflected light and radio echoes to map the electrical properties of planets it passes. A volcanic winter, even a mild one, would change those echoes. It would cool the surface, alter cloud formation, and sprinkle the ionosphere with those new ionization patterns tied to the aerosol layer. To any distant observer, Earth's spectral fingerprint would shift toward a more muted, more chaotic state, as if the planet were wrapping itself in noise. Of course, from a conventional standpoint, nothing here requires intention. Volcanoes erupt because magma rises. Aerosols cool the climate because physics says they must. If 3I Atlas plays any role, it is as an unthinking magnet and conductor nudging a delicate system. Yet even without a conscious Earth, the effect resembles an immune response. A foreign stimulus arrives, the body heats or chills, fluids surge, and barriers thicken. The organism does not need to think to react. It only needs to follow its wiring. The open question, the one that lingers after the models are run and the graphs are smoothed, is about timing. If global aerosol levels climb in the months around the December 19th close approach of 3I Atlas, if the sky grows measurably hazier while the visitor is near, do we treat that as coincidence or as part of a broader, electrically mediated conversation between space and stone? How many overlapping cycles must align before our language shifts from random cluster to systemic pulse? For those of you listening in the dark, perhaps near a window, the practical advice is not to fear the sky, but to notice it. If sunsets feel more intense, if the edge of the sun seems slightly dimmer on certain days, you are watching the atmosphere think in slow motion. Whether that thought is about 3I Atlas or about its own internal balances is a matter of interpretation. What matters for your life is that the changes will arrive as softness, haze, color, a slight veiling of the stars. We begin this section with the idea of Earth raising a shield. In the next, we turn to the largest source of energy in this system, the Sun, and ask whether our star is a bystander in this story, or whether it too is being pressed into service as a proxy, receiving the touch of 3I Atlas and sending the consequences our way in light, plasma, and charged particles that drive the very reactions we have been tracing. In public space, weather bulletins, the sun is usually the main character. Diagrams show a bright star flinging arcs of plasma outward. Labels mark X-class flares in clean fonts, and the story stops there, at the surface of fire. The quiet assumption is that whatever troubles our planet begins and ends on the sun itself. The orthodox script is simple. Magnetic fields at the solar surface twist and tangle as hot plasma moves. When the tension becomes too great, field lines reconnect, releasing stored energy in a sudden flash of X-rays and charged particles. We call the most intense of these outbursts X-class flares, and we rank them with numbers as if they were earthquakes, forgetting that the scales involved make our largest volcanoes look like sparks from a match. Over the past months, as 3I Atlas has drifted deeper into the inner solar system, the number and timing of strong solar events have become a topic of careful, if cautious, conversation. On official channels, the increase is described as part of the natural rise towards solar maximum, a familiar crest in an 11-year cycle. Off the record, some solar physicists have begun to circle dates on their calendars, marking those flares that did not quite fit the models, the ones that erupted from regions that seemed, hours earlier, merely restless rather than primed. The pattern that emerges in some of those private plots is subtle but not invisible. Certain X-class flares appear shortly after 3I Atlas crosses particular magnetic longitudes, sections of the heliospheric current sheet where the polarity of the sun's field flips. It is as if the passage of a highly conductive, fast-moving hull through those regions adds just enough extra stress to tip coronal loops from tense to tearing, peeling them open in sudden flashes that instruments detect as solar storms. In this reading, 3i Atlas does not need to be close to the Sun in a spatial sense to matter. It only needs to sit in the right part of the Sun's extended magnetic anatomy, grazing the same invisible surfaces that store the energy for flares. The hull and the 5 million kilometer plasma tail act like a moving knot in a rope of magnetism. As the knot passes, it yanks on field lines that thread back to active regions on the solar surface, encouraging them to snap back more violently than they otherwise would. Imagine the Sun as a vast, glowing drum, its surface vibrating with slow waves of magnetism. Normally, those waves crash into one another according to the star's own internal rhythms, creating flares where the interference is strongest. Now imagine 3i Atlas as a small but precisely timed tap on the edge of that drum, arriving again and again at moments when certain modes are already near resonance. The tap itself is tiny compared to the ocean of energy in the star, yet it can coax particular notes into being. When those notes take the form of X-class flares, the consequences propagate far beyond the corona. Each flare launches pulses of high-energy radiation and, often, clouds of plasma known as coronal mass ejections. These clouds race outward at hundreds of miles per second, sweeping past the orbits of Mercury and Venus, then slamming into Earth's magnetosphere hours or days later. We see the impacts as auroras, as geomagnetic storms, and as the kind of induced currents that slip through our grids and into the crust. From a conventional perspective, this is a closed loop. The Sun builds tension, releases it, and the planets cope. In the extended file, the loop becomes a chain. 3i Atlas perturbs the solar field. The Sun responds with flares and ejections, and those ejections, in turn, drive currents and reverse piezoelectric effects in Earth's crust, waking magma and stressing faults. The visitor does not need to reach out directly to touch our planet. It can press one key on the star and let the star's voice do the rest. Somewhere between these two stories, in meeting rooms with no cameras, scientists and officials struggle with the temptation to connect dots. A leaked slide deck might show plots of flare intensity overlaid with the evolving position of 3i Atlas, each flare marked not only by date and class, but by the relative angle between the visitor, the Sun, and Earth. Notes in the margin could mention statistical significance in cautious language, followed by reminders that correlation is not proof and that public communication must remain conservative. There is another thread that runs through those hypothetical notes. If 3i Atlas is capable of nudging the Sun into specific patterns of activity, then our star becomes a kind of amplifier. A modest perturbation at the level of the heliospheric field is translated into massive emissions that affect every orbiting body at once. Earth, in that case, is not a chosen target. It is one of several receivers sitting in the beam of a signal shaped by the interaction between a star and a metallic interstellar hull. For us on the ground, blaming the Sun is comforting. Solar storms are familiar villains. We have tables of historical events, from the 19th century telegraph fires to late 20th century blackouts, that let us place new disturbances in context. It is easier to say that the Sun is entering a lively phase than to admit that something from outside the solar family might be tugging on its magnetic strings and, indirectly, on ours. Yet the timing continues to nag. When a cluster of flares erupts from regions that telescopes judged stable only a day before, when the most intense X-class events align not only with internal solar cycles, but also with the path of 3I Atlas through specific magnetic sectors, the comfortable narrative begins to fray. Are we simply witnessing a noisy star at play, or are we watching a coupled system in which a conductive visitor is quietly writing a new stanza into the sun's cycle? The imaginative leap is straightforward and unsettling. If an advanced civilization wanted to influence conditions on a distant planet without approaching it too closely, using its star as a relay would be efficient. A hardened shell like 3I Atlas, tuned to interact strongly with magnetic fields, could provoke controlled flares and ejections by making small, well-timed perturbations in the stellar environment. The resulting storms would seem, to local observers, like natural variability, even as they carried out a program scripted from afar. Even without intention, the effect is similar. The presence of 3I Atlas may be turning our star into an unwitting accomplice, amplifying a magnetic disturbance that then cascades down to the surface of Earth as volcanic pulses and strange atmospheric changes. In that view, every aurora that brightens high-latitude skies over the coming weeks is both a beautiful light show and a signature of a deeper interstellar interaction unfolding above our awareness. As you listen to this, perhaps remembering nights when the northern or southern lights have shimmered overhead in pale curtains, it is worth holding both possibilities at once. The sun may simply be restless on its own, or it may be responding, faintly and involuntarily, to the passage of 3I Atlas through its extended field. In either case, the light that dances in our sky is part of a larger exchange of energy, one that does not stop at the edge of the atmosphere, but reaches into rock. In the next part of our journey, we will bring that focus back down, from the star that bathes us to the crust beneath our feet. We will look more closely at just how thin and fragile that crust really is, and how little extra stress is required under the breath of an energized sun to turn solid ground into something that moves and, in some places, flows. Most of us live as if the ground were the most reliable thing in our lives. We accept that weather is changeable, that politics shifts and markets lurch, but the idea that the street under our feet could move or soften belongs, for most people, to disaster movies. To understand what the recent volcanic spikes might really mean, we have to put that comfort aside and look at what the Earth's outer shell actually is. If you could slice the planet open like a piece of fruit, the crust would be the thinnest rind you can imagine. Under the oceans, it is only a few miles thick. Beneath continents, it thickens to a few tens of miles. Compared to the nearly 4,000 miles from surface to core, that shell is almost laughably thin, a painted glaze on a deep, hot interior. Every city, every road, every quiet bedroom listening to this now is perched on that glaze. Beneath Mexico City, Jakarta, Addis Ababa, Honolulu, and countless other places, that glaze is cracked. The crust is broken into plates that move slowly over a softer, ductile layer we call the asthenosphere. Those plates grind, dive, and scrape past one another along faults that may cut all the way through the brittle shell. Where one plate dives beneath another, magma can rise, feeding the volcanoes that have been lighting up our maps since 3I Atlas entered the inner system. Under active volcanic arcs, the situation is even more delicate. There, the crust is both thicker and more fractured, riddled with cooled intrusions, old dikes, and still molten reservoirs. Magma does not sit in a single, neat chamber. It occupies a hierarchy of pockets and sills connected by narrow conduits, some barely wider than a city block, others thin as a street. When pressure in one segment changes, the entire network can feel it. Geophysicists sometimes compare this system to a mountain range of glass resting on rubber. The glass seems solid until you push it in just the right way. Then hairline fractures propagate at astonishing speed, redistributing stress from one ridge to another. In the crust, those pushes come from the slow motion of plates, from the rise and cooling of magma, and from changes in the weight of water and ice at the surface. What we have been exploring is the idea that there is another push available, one that comes from changes in the electromagnetic environment driven by 3I Atlas. In purely mechanical models, a fault ruptures when the accumulated shear stress exceeds the strength of the rock. The difference between locked and slipping can be small. In some regions, laboratory experiments and field data suggest that a few percent change in effective stress is enough to trigger failure. The same is true for some magma systems. A minor increase in gas pressure or a slight weakening of the surrounding rock can decide whether melt stays confined or finds a path upward. If induced currents from a disturbed magnetic field are flowing through the crust, and if they are interacting with quartz-rich rocks via the reverse piezoelectric effect, then those currents become one more way to deliver that crucial few percent. Tiny expansions and contractions at the microscopic level translate into changes in friction along faults and in the walls of magma conduits. The stress map under a volcano does not shift by a mile. It shifts by millimeters where it matters, on surfaces already poised at a threshold. Consider a city built on soft, water-saturated sediments above a subduction zone. The deeper fault carries the main tectonic load, but the shallow layers determine how the shaking feels. During strong earthquakes, those sediments can liquefy, behaving more like a heavy fluid than a solid, allowing buildings to list and sink even if they do not collapse. That liquefaction is usually framed as a purely mechanical response to shaking. Yet the same conductive, water-rich layers are also prime candidates for hosting induced currents during geomagnetic disturbances. Now place that city in the time frame we have been tracing. The sun, possibly nudged by 3I Atlas, fires off a series of energetic flares. The resulting storms twist Earth's magnetosphere, driving subtle currents along plate boundaries and through those shallow, saturated sediments. At depth, quartz grains flex and crackle under the reverse piezoelectric effect. Nearer the surface, small changes in pore pressure and grain contact alter how easily the sediments could liquefy when the next significant tremor arrives. To the residents, any later shaking will be blamed on an earthquake. The electromagnetic preconditioning, if it exists, will remain invisible. One of the unsettling lessons from past disasters is how far damage can extend from epicenters. Cities hundreds of miles from a fault have seen buildings topple because local geology amplified the waves. In the context of an electrically sensitive crust, that amplification could be more than a passive property. It might be a state that can be tuned slightly by external fields. A small change in magnetic conditions, coinciding with the path of 3I Atlas through a favorable sector of the heliospheric field, could make some basins a little more ready to slosh. This is where the phrase, electromagnetic earthquake begins to appear in private notes, not as a claim that 3i Atlas is firing beam weapons at our cities, but as a suggestion that some of the stress changes we usually attribute to internal dynamics alone might be synchronized gently by external modulation. A planet with a thin, cracked shell immersed in a changing magnetic sea will not respond only to what happens in its own mantle. It will also respond to whatever large, conductive bodies pass through the larger field that contains it. The psychological weight of this is easy to underestimate. It is one thing to accept that we live on moving plates above a deep, hot interior. That story is now part of school books and museum displays. It is another thing to accept that the solidity of the ground might also depend on a visitor we can barely see, a nickel-bright hull and plasma tail named 3i Atlas, threading an orbit millions of miles away. The floor of your room begins to feel less like an isolated surface and more like the skin of a body connected to currents far beyond the horizon. If you could stand in a transparent shaft that extended from your house down through the crust, you would see only a few tens of miles of solid rock before the view gave way to glowing plastic mantle. The line between your feet and that glow is thinner than the distance you might drive in an afternoon. Every fault, every magma pocket, every conductive vein of mineral between you and that glow is part of a system that can be nudged, not only by the slow drift of continents, but also by the way the planet is being wired, briefly, into the path of 3i Atlas. From the perspective of deep time, this fragility is not new. The crust has always been thin, always been fractured. What is new in our story is our awareness and the coincidence of that awareness with the passage of an interstellar object that behaves less like an icy wanderer and more like a moving piece of machinery embedded in the sun's magnetic field. The same calculations that let us build inductors and transformers whisper that we may now be sitting inside one. As this section closes, the image to hold is simple. A child running across a city square, a commuter train crossing a bridge, a farmer walking along the flank of a volcano. Each step lands on a film of rock suspended over a deep, moving interior, and that interior is being ever so slightly retuned by currents flowing in from the sky. The ground feels stable because our senses are slow compared to the processes reshaping it. In the next part of our journey, we will test that sense of stability against memory. We will leave the immediate tremors and eruptions of this year and read the scars written into old lava flows and buried sediments, asking whether the awakening of Ethiopia's long, silent volcano and the global pulse we are tracing might be echoes of an encounter that happened once before, thousands of years ago, when another chapter of Earth's thin crust was peeled back and rewritten. There is a strange kind of memory that does not live in brains or books. It lives in stone. It lives in the way a continent is cracked, in the chemistry of buried ash, in the quiet, repeating habits of ice and fire. When we speak of a 12,000-year marker, we are really asking whether Earth remembers something that our written history has forgotten, and whether the pulse we feel now is an echo of a much older encounter. The newly awakened volcano in Ethiopia is not just a local hazard in that frame. It is a clock. Its last major eruption took place near the end of the last ice age, at a time when glaciers still lay heavy on the northern continents and sea levels hovered far below their present heights. Radiometric dates cluster around that transition from glacial cold to a brief, brutal return to near glacial conditions, a climatic whiplash that scientists now call the Younger Dryas. The same vent that has waited quietly through the entire span of agriculture and cities last spoke when the world was in the middle of that upheaval. The Younger Dryas is one of the clearest scars in recent climate history. Temperatures in the North Atlantic region dropped sharply in a matter of decades, not in the slow, stately swing we expect from orbital cycles. Ice sheets stabilized, then advanced. Vegetation patterns snapped back toward tundra. In lake sediments and ice cores, you can see the shift as an abrupt change in layers, a thin boundary where one pattern stops and another, harsher one begins. Around that boundary, geologists also find something else. Charcoal, tiny spherules of melted rock, odd enrichments of platinum, and other metals that do not always fit cleanly into the story of simple, gradual change. Mainstream explanations for this episode range from massive meltwater floods disrupting ocean currents to the after effects of one or more large impacts by fragments of a comet. Papers argue back and forth over which mechanism fits which proxy record best. No single solution has settled the debate. What remains undisputed is that near 12,000 years ago, something kicked the climate and the crust hard enough to alter the trajectory of both. Volcanoes responded. Ice responded. Ecosystems and early human cultures responded. From the perspective of our current story, that uncertain cause becomes the gap where 3I Atlas can be inserted as a suspect. We know that objects can pass through the inner solar system on long, looping paths measured in tens or hundreds of thousands of years. We also know that our instruments have only watched the sky with any rigor for a very short slice of that span. If an interstellar object with a conductive hull and a strong magnetic signature crossed the plane of the planets 12,000 years ago, we would not have telescopes to mark it. We would have only ash, ice, and oddly timed eruptions. The Ethiopian volcano's last awakening near that boundary is then more than a coincidence. It is a candidate marker. Under the African superplume, the mantle was already rising, already hot, already close to critical thresholds. A foreign magnetic stress passing through the heliospheric field could have added the final few percent, just as we suspect it may be doing now. The plume flared, the vent opened, ash rose into a sky already troubled by dust and shifting winds. When that stress faded, the system cooled and quieted. The vent slept. The memory stayed in the rock. If we read other records from that time with the same eyes, more pieces begin to line up. Ice cores from Greenland and Antarctica show not just temperature changes, but spikes in acidity that hint at increased volcanic activity. Lake beds in different continents preserve thin, dark layers rich in soot and microscopic glass, as if fire and rapid melting stalked the landscape together. Some archaeological sites show abrupt breaks in habitation, followed by different tool styles and new settlement patterns, as if groups were forced to move or adapt in the wake of environmental shock. None of this proves that an object like 3I Atlas was involved. It does, however, outline the kind of global response a strong external perturbation can produce. Climate tips into a new state. Volcanoes pulse more often. Ice sheets fracture and retreat in lurches instead of smooth curves. Species vanish. New niches open. The phrase geological reset is not poetic in that context. It is a literal description of a system being jolted into a different equilibrium, one in which the patterns of the previous tens of thousands of years no longer apply. The speculative question that follows is almost unavoidable. Could 3i Atlas be returning, not as a first-time visitor, but as part of a longer cycle that brushes past the inner system every 12,000 years or so? Classical orbital mechanics argues that truly interstellar objects are on open, hyperbolic trajectories. They do not return unless something massive alters their path. Yet we also know that gravity and magnetic fields can do strange work over great distances, especially if an object passes near other massive bodies that we have not yet cataloged or fully understood. It may be that 3i Atlas is not the same individual visitor that passed near Earth during the Younger Dryas, but a member of a family. A stream of conductive fragments moving through our region of the galaxy, their arrivals spaced by tens of millennia. From the standpoint of geological time, such arrivals would still look like a cycle. Every so often, the field changes. Every so often, Earth feels a new kind of magnetic pressure and responds with pulses of ice, fire, and rearranged climate. The planet keeps time with encounters, not just with orbital wobbles. Imagine, for a moment, a human standing on the edge of a receding ice sheet 12,000 years ago. The air is clear and cold. The stars at night are the same, yet subtly different in their positions. Above the horizon, strange curtains of green light flicker more often than ancestors remember. Ground tremors roll underfoot in ways that elders describe as new. There are no satellites, no magnetometers, no digital archives. There is only a sense that the sky and the ground have started to speak with the same uneasy rhythm. That person might carve stories into bone or stone, tales of the day the rivers changed, or the season when ash fell on snow. Those stories pass through generations, losing detail and gaining symbol, until they become myths of angry skies or gods that shake the mountains. Meanwhile, the hard record of what actually happened stays locked in sediments and frozen layers, waiting for microscopes and isotope counters. When we finally develop those tools, we read the record and give the episode names like Younger Dryas. We rarely ask whether the myth and the record describe different faces of the same event. Today, the situation is inverted. We have instruments that can track 3i Atlas across the sky in fine detail, measure its speed, infer its metallic nature. We have global networks that log every tremor and every volcanic plume. We watch the sun, the magnetic field, the oceans, the atmosphere. What we lack is the long view. Our high-resolution movie covers only a few decades. The previous frame that might resemble this one is 12,000 years behind us, blurred and scratched, written not in pixels, but in ash. When the Ethiopian volcano woke again, it put a mark on that movie that is hard to ignore. It is the same vent, in the same tectonic setting, reacting strongly in two episodes separated by roughly the span between the Younger Dryas and now. That does not guarantee an identical cause, but for those inclined toward pattern recognition, it suggests that the planet may have its own way of underlining certain chapters. A vent that erupts at both markers is effectively circling the dates in fire. Are we living through the opening scenes of another reset of similar scale, or only through a smaller aftershock in a complex, internally driven system? Is 3i Atlas the hidden line connecting the two pulses, or merely a coincidental visitor arriving while old, slow cycles reach their natural crest? The safest answer is that we do not know. The more honest answer is that the combination of timing, volcanic spikes, and an electrically potent interstellar hull moving through our environment makes ignorance feel less comfortable than it used to. What we can say is that Earth has already demonstrated its capacity to reorganize itself sharply when pressed, and that it carries those episodes as clear signatures in stone and ice. The 12,000-year marker is one such signature. The fact that a long, silent volcano beneath the African superplume chose this year to speak again aligns the present with that past in a way that is hard to unsee. Whether that alignment is coincidental or causal, it changes how some of us read the news. In the next part of this journey, we will lean fully into the idea that Earth is not simply a passive rock reacting mechanically, but a complex, self-regulating entity with instincts that may not always be gentle. We will explore the darker edge of Gaia, the possibility that the pulses of magma and ash we are witnessing are not just byproducts of stress, but deliberate pressure releases from a planet that has learned, over deep time, how to survive foreign currents, like the one that 3i Atlas may be bringing now. There is a gentle cruelty in the idea that the world beneath your feet might have its own instincts. Not the kind that think in words, but the kind that twitch, adjust, and sacrifice pieces of themselves in order to survive. When people speak about Gaia, they usually mean the soft version of that instinct. Tonight, we sit with the darker one. The original Gaia hypothesis grew out of chemistry and feedback loops. It suggested that life and the non-living parts of Earth form a coupled system that tends, over long spans of time, to keep conditions within a range that liquid water and biology can tolerate. Oceans buffer carbon dioxide, forests draw down excess carbon and release oxygen, weathering removes greenhouse gases when the planet grows too warm, while volcanic outgassing replenishes them when it grows too cold. In this view, Gaia is less a goddess and more a thermostat. Dark Gaia keeps the physics, but changes the mood. It asks what happens when the same self-regulating system is pushed into a corner, the way a body that normally keeps a steady temperature will also sweat, shiver, and inflame a wound. Over geological time, volcanoes have helped stabilize the climate by releasing gases that warm a frozen world and by building mountains that later erode and draw carbon out of the air. Yet the same eruptions that balance heat have also driven mass extinctions, flooded continents with lava, and darkened skies for years. In a dark Gaia frame, volcanoes are the pressure valves of a nervous system that has learned by trial and error that it is better to vent violently in some places than to let strain accumulate everywhere at once. Now imagine that this system is not only mechanical, but also electrically sensitive. In previous episodes, we explored how the crust, rich in quartz and conductive fluids, can respond to induced currents through the reverse piezoelectric effect, and we traced a route by which the metallic hull and plasma tail of 3i Atlas could inject new patterns of current into that crust via the sun and the magnetosphere. Dark Gaia asks what the planet does with that extra stress once it arrives. One possibility is passivity. The currents seep in, rocks flex, some volcanoes happen to be near failure and are nudged across their thresholds. That is the minimalist story. The more haunting possibility is that the coupled system of mantle, crust, ocean, atmosphere, and biosphere behaves more like a body under a new kind of load. It senses, in a distributed way, that certain regions are more vulnerable than others. And it chooses, in a purely physical sense, to relieve pressure along paths that minimize overall damage to its long-term functioning. In that picture, the African superplume, the Ring of Fire, and other magmatic hotspots become not just weak points, but preferred release routes. They are scars that have been opened before, tested channels for heat, gas, and perhaps electrical discharge. When currents associated with 3I Atlas raise the internal tension, these regions respond first because the wiring of the system has already been carved to favor them. The planet sacrifices stability around certain volcanoes so that the deeper architecture can remain intact. The hard science that underlies this idea is the study of negative feedbacks. Climate models already include processes where warming increases cloud cover or plant growth, which then limit further warming. Deep Earth models include ways in which increased mantle temperature can speed up plate motion, which in turn helps vent heat more efficiently. Dark Gaia extends that same logic into the electromagnetic domain. If induced currents from the passage of 3I Atlas threaten to raise stresses across broad regions of the crust, then erupting a subset of volcanoes may be the cheapest way, in energy terms, to restore balance. Opening vents releases gas, heat, and perhaps charge. It changes the conductivity structure of the crust and atmosphere above those points, creating new pathways for current to leave the system instead of continuing to build inside it. Visualize an Earth for a moment, not as blue marble, but as a slowly breathing animal covered in glowing capillaries. Superplumes rise from the deep mantle like arteries. Volcanoes sit at their ends as pores. As 3I Atlas approaches, a faint foreign current begins to circulate through this network. The capillaries brighten. In a few locations, the pressure crosses an internal threshold, and the pores flare, spraying magma and aerosols into the sky. To us, that looks like disaster. To the animal, it is closer to sweating out a fever. We see echoes of this behavior in the geological record. Large igneous provinces, those immense outpourings of basalt that cover vast regions, often coincide with climatic upheavals and biological crises. Yet after the lava cools and the gases disperse, the system settles into a new, sometimes more stable state. The crust is thicker in some places, thinner in others. Circulation patterns in the mantle shift. The organism has scarred and survived, and life repopulates the edges of the wounds. In the HN frame, 3I Atlas becomes a new kind of infection. Its metallic hull and induction effects introduce stresses that do not fit the familiar patterns of orbital cycles or internal convection alone. Dark Gaia asks whether Earth, faced with that pattern, is now choosing a strategy that looks like fever and controlled bleeding. Frequent, moderate eruptions, scattered around key arcs and plumes, may prevent the kind of planet-wide rupture that would threaten the deeper integrity of the system. Of course, we must be careful with words like fear and anger. The planet does not feel in the way a person does. Its responses are encoded in physical laws, not in stories. When we say Gaia is frightened or Gaia is angry, we are naming our own reaction to the scale and violence of its adjustments. The usefulness of the metaphor lies in reminding us that these adjustments are not random. They are shaped by feedbacks that have been refined over billions of years. Still, the metaphor can guide questions. If Earth responds to 3I Atlas as a body to a pathogen, what symptoms should we expect to see? A rise in volcanic activity is one. Shifts in atmospheric chemistry that alter how easily energy and information can enter or leave the system are another. Changes in ocean circulation that redistribute heat away from vulnerable regions may be a third. Each of these is observable, at least in principle, with the instruments we have already launched and the networks we have already built. Viewed this way, the current pattern of eruptions, the strange hums under the oceans, and the slightly erratic behavior of the geomagnetic field begin to resemble a coordinated response rather than a series of disconnected accidents. The system is moving heat, charge, and stress away from places where they would do the most long-term damage and into channels where they can be released in forms that look catastrophic to us, but useful to it. The unsettling part of dark Gaia is not that Earth might defend itself. It is that our presence does not figure prominently in that defense. A fever does not consult the comfort of individual cells. It raises the temperature because, on average, that tactic has allowed past organisms to survive similar threats. If the planet is in such a mode now, responding to the electromagnetic presence of 3I Atlas, then our cities near volcanoes and coasts may be positioned, quite literally, on the sacrificial surfaces. For those lying awake at night listening to distant rumbles or watching news of ash and lava, this perspective can cut both ways. On one hand, it suggests that the violence we see is not meaningless, that it is part of a coherent attempt by the system we live within to absorb a foreign pulse. On the other hand, it reminds us that the priorities of that system are not aligned with our convenience. We are passengers on a body that will choose survival over comfort every time. As this part of the file closes, the question left hovering is simple and heavy. If the pulses we are recording now are the early stages of a dark Gaia response to 3I Atlas, how far will the system need to go before it considers the threat managed? Are a few synchronized eruptions enough, or are we watching the first beats of a longer, deeper adjustment that will redraw coastlines, climates, and the quiet map of where it is safe to sleep? In the next segment, we will narrow our focus from global patterns to local omens, looking at strange colors in the sky, unexplained glows, and electrical tingles reported near active volcanoes, and asking whether these fleeting lights might be the closest thing the planet has to a spoken warning before it opens another of its pressure valves. Before many eruptions, the first thing to change is not the sound, but the color of the world. Long before sirens, before official alerts, there are stories of evenings when the clouds over a quiet volcano turn an unnatural violet, or when a greenish band appears low on the horizon with no aurora forecast, no storm in sight. To most, these are just strange sunsets. To those who live close to the vents, they are read as omens. In villages around restless mountains, people learn to hear silence. Dogs grow uneasy for no obvious reason. Insects vanish from the usual lamps. Radios pick up faint, wavering static even on clear nights. Somewhere in that tension, someone will step outside to hang laundry or smoke a last cigarette and notice that the hair on their arms is lifting as if a storm were about to break, even though the air is perfectly still. Science has a language for some of these apparitions. Earthquake lights have been documented in a handful of cases, pale glows along fault lines, flickering orbs near cliffs, broad sheets of luminosity that bloom just before or during strong quakes. Near active volcanoes, observers sometimes report halos above the summit or diffuse glows along ridges at times when gas emissions and ground deformation are already elevated. Instruments, when they happen to be watching, capture spikes in local electric field strength, bursts of low-frequency radio noise, and short-lived changes in the conductivity of the air. At the simplest level, these effects trace back to ionization. When the electric field between ground and sky becomes strong enough, it can strip electrons from air molecules. Excited oxygen and nitrogen then release light as they relax, painting the sky in soft greens, blues, and purples more often associated with auroras. Near erupting vents, rising columns of ash and gas can carry charge as well, creating their own miniature storm systems, with lightning crawling inside plumes like nerves firing in a wound. The crust beneath such displays is rarely calm. As microcracks form and grow under tectonic or magmatic stress, charges can separate along newly created surfaces. Quartz-rich rocks are particularly good at this. Squeezed and flexed, they build up electric potentials that search for paths outward. When those charges reach the surface, they can leak into the atmosphere, intensifying the local electric field and shaping how and where ionization occurs. The result is a fleeting, luminous skin on an invisible electrical process. Up to this point, the story is one of internal pressure, pushing its way out. In the context of 3I Atlas, another layer appears. If induced currents from its interaction with the sun's magnetic field are flowing into the crust along deep conductive paths, they will not stop at the mantle. They will curl upward wherever the rock is fractured and gas-laden wherever the resistance is lowest. Volcanoes, with their open conduits and fluid-rich surroundings, become natural chimneys not only for heat and magma, but also for charge. The sky above them becomes the place where foreign currents are most likely to show their faces. Imagine standing on a slope below such a volcano on a night a few weeks from now. The usual stars are visible, but their sharpness is softened by a faint, high haze from distant eruptions. As you watch, a dim, greenish band appears just above the summit, too low and too localized to be an aurora in the conventional sense. For a moment, it brightens, as if some unseen filament has connected peak to sky, then fades, leaving the air with a metallic scent and your phone with a briefly frozen screen. The next morning, seismic charts will show that tremors increased shortly after that glow. To the scientist who has instrument arrays on those slopes, nights like this are both gift and torment. Electric field meters will record sharp, transient pulses. Magnetometers may show tiny, abrupt deviations. Very low frequency receivers, the kind used to listen for lightning on the far side of the world, may capture new, curious chirps. Each dataset can be explained in isolation as local weather, as lightning, as man-made interference. When laid over the timeline of magmatic unrest and the position of 3I Atlas in the sky, they form a more unsettling picture. Someone quietly tapping the glass from the outside and the rock answering with light. It is here that dark Gaia and the declassified file meet. If Earth is using volcanoes as pressure valves to bleed off stress from the currents tied to 3I Atlas, then these strange lights and tingling fields may be the nearest thing it has to spoken warnings before it opens another vent. The planet cannot put words in our ears. It can only change the spectrum above our heads, the feel of the air on our skin, the reliability of the devices we keep in our pockets in the hours before magma rises. Official narratives handle these stories with care, when they handle them at all. Reports of purple skies and pre-quake glows are cataloged, then filed under atmospheric optics, unconfirmed anecdotes, or rare phenomena still under study. Explanations lean toward distant lightning reflected in clouds, urban light pollution scattered in unusual ways, camera sensors pushed beyond their design limits. None of these are impossible. They simply steer attention away from the idea that the ground and the sky might be sharing current in a way that involves 3I Atlas. For those who live close to active mountains, the classification matters less than the pattern. They remember the night when their teeth tasted faintly of pennies, when cats hid and the television crackled, and how, a day later, a fissure opened on a flank and a new curtain of lava appeared where there had been only scrub and rock. They talk quietly about those nights in markets and on buses, not as abstract science but as practical information. When the sky turns that color again, be ready to move. In the language of this investigation, those experiences become data points in a map of premonitions. Each report of odd glows, each instrument log showing a sharp electric spike, is tagged with time, place, and the evolving track of 3I Atlas. Patterns begin to emerge in that combined map, clusters of warnings in certain longitudes as the visitor passes through aligned sectors of the heliospheric field, repeated signatures in electric noise, preceding eruptions tied to the same deep plumes and subduction zones. The open question is not whether these warnings exist. Enough independent records now suggest that the crust and atmosphere do sometimes behave strangely before major releases of energy. The question, in the shadow of 3I Atlas, is what exactly they are warning about. Are they simply the last shivers of an internally driven system adjusting itself? Or are they fringe effects of a larger foreign current passing through, the glow at the edges of a circuit being overloaded by an approaching hull and tail? As you listen to this, perhaps you can call to mind your own sky. Have there been nights recently when clouds looked subtly wrong, when static seemed to link to clothes and door handles, when storms behaved outside their usual patterns? Most of these memories will have ordinary explanations. A few may not. In a world without 3I Atlas, those would be curiosities. In a world where a metallic interstellar object is threading the sun's magnetic field and coinciding with global volcanic spikes, they start to feel like soft knocks on the underside of the atmosphere. This chapter closes with an image that blends stone and light. A volcano in the dark, its summit still unbroken, outlined against a sky that has taken on a faint electric hue. In the soil around it, sensors quietly registering rising currents. Above it, unseen lines of magnetic force bending under the influence of a distant, bright speck named 3I Atlas. Between them, for a few minutes, the air glows in colors that have no simple name, as if the whole system were drawing a breath before speaking more loudly. In the next and final section of this file, we will step from omens to timing. We will ask what it means for all of these pulses, glows, and tremors to be unfolding while 3I Atlas is still relatively far away, and what kind of planetary response might be possible or necessary when December 19th arrives and the visitor's influence reaches its peak. There is a shift that happens when you realize the story you are watching has not yet reached its loudest note. Everything we have traced so far, from Ethiopian fire to ocean hums and violet skies, is happening while 3I Atlas is still, in astronomical terms, far away. The question that opens this final section is quiet and sharp. If this is only now, what does close look like? At the moment, 3I or Atlas is still tens of millions of miles from Earth, moving along its inbound curve with a measured, relentless speed. Telescopes track its position to within small errors. Models show that on December 19th, it will pass at a distance that poses no direct impact risk, a clean miss for rock and ice, a statistical non-event for gravity. On paper, it is safe. On paper, you could sleep through that night without knowing anything had happened. The fields do not read those papers. What matters for the planet's electromagnetic state is not only how close 3I Atlas comes in kilometers, but how its metallic hull and long plasma tail line up with the Sun, Earth, and the sprawling current sheet that ties them together. There are certain geometries that maximize induction, turning even modest relative motions into efficient generators. The days around December 19th are when those geometries stack, not in one sharp instant, but in a slowly tightening knot. If the induction coil model we have followed is even partly correct, the coming peak is less about a single trigger and more about a span of time when added current will be hardest to avoid. Earth will rotate through the wake of 3I Atlas again and again. Each turn will drag different arcs of crust, ocean, and ionosphere through slightly altered magnetic gradients. From the planet's point of view, it will feel less like one big impact and more like weeks of small, repeating pushes. In that light, the recent volcanic spikes and synchronized tremors take on a different mood. They are no longer the storm, but the first drops of rain on a window. Ethiopia, the ring of fire, the infrasound hum of the oceans, the strange electric glows over certain summits, all of these may be the system's early responses to a foreign current that has only just begun to rise. If that is true, then December is not the surprise. December is the crescendo of a song already playing softly underneath our days. What might that crescendo look like? One possibility is simply more of the same, but denser. More volcanoes entering restless phases, more small earthquakes in regions not known for them, more reports of whales changing course and skies shifting color before local events. The pattern would be global and uneven, sparing some regions entirely, while focusing on others that happen to lie along favored paths of conductivity. From a human perspective, it would feel like a rough season, but not an ending. A more severe scenario, the one that appears in the margins of internal forecasts, involves the idea of electromagnetic earthquakes becoming more frequent in places where tectonic maps show no major faults. In that picture, stresses that would normally dissipate quietly in the ductile mantle are given extra structure by induced currents, channeling energy into brittle patches of crust that engineers assumed were safe. Tremors rattle cities built far from plate boundaries. Old dams and power plants feel strains they were not designed to share. Threaded through all of these possibilities is the question of resonance. Every complex system has frequencies at which it responds most strongly. If the spectrum of disturbances associated with 3I Atlas, from slow magnetic undulations to higher frequency pulses like the one near 2.4 gigahertz, happens to line up with some of Earth's own natural modes, then even small inputs could build over time. The result would not be a single dramatic day, but a season during which the crust seems to vibrate in sympathy with something outside the sky. Visually, December 19th itself may pass like any other night. The closest approach does not guarantee auroras at the equator or fire falling from space. You might look up and see only the familiar stars, or clouds lit by city glow. Yet in magnetometer logs and strain gauges, the date could stand out as a gentle kink, a bend in lines that had been climbing more slowly, a moment when the invisible load on the planet's shell reached a temporary high before easing. For those who design satellites and power grids, this is already a planning problem. Quiet advisories circulate, framed in careful language about heightened space weather risks during an interval that just happens to overlap with the passage of 3I Atlas. Operators rehearse how to switch systems into safer modes if geomagnetic storms intensify. Most of these precautions will look, to the public, like ordinary prudence during an active solar phase. Only a few will connect them to the metallic hull sliding through the sun's field. For everyone else, the coming peak is less about hardware and more about psychology. We live in bodies that like certainty. We prefer our ground to be inert, our sky to be decoration. To be told that an interstellar object may be altering the deep behavior of the planet, not through impact but through induction, is to be reminded that our sense of separation from cosmic events has always been a comforting illusion. The Earth is wired into its environment. We are wired into Earth. The imaginative leap that some will quietly make is simple. They will picture December 19th as a kind of planetary scan, a moment when 3I Atlas takes a full reading of how this crust, this atmosphere, this magnetic envelope respond to the current it carries. Every volcano that coughs, every ocean basin that hums, every fault that slips adds another line to that reading. Whether the visitor is an unconscious conductor or a deliberate probe, the result is the same. Our world will have spoken its response in fire and motion. The open question that lingers as we move toward that date is not whether something will happen. Something is already happening. The question is how far the system will be pushed before the foreign current fades, and how much of that push will be stored as new stress in rock and ice rather than released as ash and light. When 3I Atlas has gone, will we be able to say that the planet's pulse merely quickened for a moment? Or will we look back and recognize this season as the start of a longer, quieter rearrangement? As this chapter closes, the advice is not to fixate on a single night, but to pay attention to the pattern. Notice how often the words volcano, tremor, magnetic, and aurora appear together in headlines and local stories. Notice, too, the way your own body reacts to the idea that the ground is participating in a dialogue with something you cannot see. In the next segment, we will turn from prediction to preparation, not in the sense of stockpiles, but in the gentler sense of grounding, of learning how to stay emotionally steady on a planet that may be preparing to shake a little harder under the influence of 3I Atlas. Preparation, in a story like this, is not about predicting the exact moment when the ground might move. It is about learning how to live on a planet that is already stirring without letting that knowledge hollow out your sleep. The first shift is quiet and internal. For most of your life, you have treated the solid parts of Earth as background, like furniture that never moves. In the season of 3I Atlas, you are invited to trade that illusion for something more honest. The crust was always thin, the plates were always in motion. The difference now is that you are aware, and the awareness comes with a new kind of responsibility to yourself, to feel the tremor without becoming the tremor. One practical way to begin is simply to learn where you stand, not in a paranoid way, but in the same tone you might use to learn a new neighborhood. Is your home on deep sediment or on older rock? Are there known faults or volcanoes nearby, even small ones? Do local agencies already publish simple guidance for earthquakes or ashfall? You are not memorizing a disaster manual. You are learning the anatomy of the ground that carries you, so that if it does shift under the influence of currents tied to Three Eyes Atlas, the sensations arrive in a landscape you recognize by name. Think of it as learning to read vital signs. Doctors listen to a pulse, not because they expect a heart to fail every second, but because knowing the normal rhythm makes any change easier to understand. In the same way, knowing how often your region usually feels tremors, how local soils behave, and how past eruptions or quakes have unfolded gives context to the news scroll of global volcanic spikes. Even in a world where electromagnetic earthquakes become more frequent than maps suggest they should, you will face them with more clarity if you already know how your own ground tends to respond. Preparation is also physical in a gentler, more literal sense. Grounding is not only a word from electrical diagrams, it is something you can do with your body. Walk barefoot on safe soil or grass and notice the texture under your soles. Sit with your back against an old wall or a tree and feel how your breath slowly synchronizes with the firmness behind you. These small practices are not magic. They will not stop plates from moving. What they do is teach your nervous system that contact with Earth can be calm, that the planet is not only a source of threats, but also a stable reference that has held you all along. The informational environment around Three Eye Atlas will not always be calm. As December approaches, graphs and predictions will multiply. Some voices will frame every flare, every tremor, every eruption as proof that something catastrophic is imminent. Others will insist that nothing out of the ordinary is happening at all. Between those poles, your task is to curate your own input. Choose one or two sources you trust to track space weather and geology. Let them be your instruments. Do not let every rumor become your sky. There is a place for simple, quiet resilience in this story. The same items that help you in a storm will help you in a flicker of ground or grid. A flashlight where you can reach it in the dark. A few days of drinking water. A small supply of essential medications. A way to keep a phone charged if the power blinks. These are not signs that you expect collapse. They are the household equivalent of keeping a coat near the door when the season turns cold. Even if Three Eye Atlas were not passing, they would still be wise. Once you have tended to those basics, you can allow yourself a more imaginative rehearsal. Picture a night when the lights go out for an hour, not because of a local storm, but because the grid is riding out a geomagnetic disturbance. Picture a few seconds of gentle shaking, the kind that rattles glasses but leaves walls intact, perhaps timed suspiciously close to a solar flare linked to the interstellar visitor. In that moment, what do you reach for first? A switch, a voice, a window. The rehearsal is not about fear. It is about discovering that even in the dark, even with the floor humming, you can still choose the next small, steady action. Another layer of preparation lives between people. As creatures who share stories, we are not meant to carry cosmic unease alone. When you tell a friend that you felt a faint tremor, or that the sky above your town looked unusually bright one night, you are not just trading anecdotes. You are building a network of attention. In a season where the whole planet may be reacting to a foreign current, conversations become a kind of sensor grid, a human counterpart to the instruments that are logging numbers in distant observatories. Communities can, in quiet ways, Decide how to respond to such a season. A neighborhood might agree on where to meet if phones fail for a day. Families might talk through how to comfort children if news of eruptions and strange auroras becomes more frequent. Friends might choose a simple check-in phrase they send each other when something unsettling happens, not to amplify fear, but to acknowledge that they are watching the same pattern and are committed to carrying it together. There is also the question of how you narrate what is happening inside your own mind. You could tell yourself that you are living under threat from a hostile object, a nickel-bright hull named 3I Atlas that has come to test the planet's weaknesses. You could also tell yourself that you are living through a phase of energy transformation, where Earth is adjusting to a new kind of external stress using tools it has always had: volcanoes, fields, and feedbacks. Both stories fit the same data. One tightens the chest, the other, while still serious, leaves room for awe. Consider what it might feel like to experience a small tremor during this season and to frame it, not as the world falling apart, but as the planet changing posture under you. The books on your shelf sway. The water in a glass ripples. Somewhere in the mantle, stress is redistributing in response to currents linked to 3I Atlas. Your role in that moment is not to control the redistribution. It is simply to breathe, to keep your awareness open, to remember that you are not separate from the system that is moving. You are part of its surface, feeling what it feels in miniature. Preparation, at its deepest level, is a matter of choosing what you will hold on to if the pattern intensifies. Some people will cling to schedules, insisting that nothing has changed until the routine becomes impossible. Others will fixate on worst-case scenarios, living through dozens of imaginary disasters for every real event. The middle path is quieter. It says, I will keep a few useful objects close. I will keep a few people closer. I will learn how my ground normally behaves, and I will accept that for a while, the planet may be louder than I am used to. There is a simple, human-sized question hiding inside the vastness of this file. If you knew that the coming months would bring more tremors, more strange lights, more news of interactions between 3I Atlas and the Sun, what would you want to practice feeling? Panic or presence? Isolation or connection? Helplessness or the small competence of lighting a candle calmly in a moving room? You cannot choose the currents that pass through rock and field. You can choose the currents you cultivate in your own nervous system as they pass. As this part of the journey closes, think of preparation not as a bunker, but as a posture. Feet on the ground, eyes open, breath slow, mind informed, but not flooded. The planet may indeed be preparing to shake a little harder as 3I Atlas reaches its peak influence. Your task is not to stop that shake. It is to be ready to listen to it without vanishing into fear. In the final chapter, we will follow that listening all the way down, away from the telescopes and the alerts, to a softer place where the most meaningful response is not to look up at the visitor, but to feel the quiet, evolving pulse of the earth under your own weight. There is a temptation in stories like this to keep our eyes fixed on the brightest object. 3I Atlas pulls attention upward. Its orbit diagrams, its metallic hull, its 5 million kilometer tail, all of these invite us to stare into the dark and search for a speck of moving light. Before we finish, it may be worth gently turning your gaze back down to the one place where you have always been in contact with the mystery. Right now, as you listen, there is a line connecting you to the center of the planet. It passes through floors and foundations, through soil and stone, through old faults and slow rivers of rock. Along that line, stress is shifting. Tiny grains are flexing, currents are wandering, magma is finding or forgetting its paths. The entire investigation you have just walked through lives along that invisible thread. From 3i Atlas in the sky, through the sun and magnetic fields, into the crust, and finally into the soles of your feet. You do not need the instruments to be part of that chain. You are already a sensor. Think of the times you have felt a low vibration in a building before anyone named it an earthquake, or the way your body relaxes when you lie down on solid ground after a long day. Your nervous system has been listening to the planet longer than any seismometer. Most of the time, the signal is simply too slow and too gentle to make it into words. If the coming weeks bring more tremors, more quiet reports of distant volcanoes stirring in unison, as 3i Atlas reaches its peak influence, you will be invited to choose how you participate. One option is to stay locked in the upward stare, scrolling through plots of orbits and flare forecasts, watching the visitor like an incoming storm. Another is to let those plots recede to the background and pay more attention to the contact between your body and the ground. You can try this in very small, ordinary ways. The next time you stand at a bus stop, or wait in line, or sit beside a window, notice the support under you. Notice how every muscle that keeps you upright is working in conversation with gravity and stone. In those moments, the drama of interstellar hulls and induction coils becomes something surprisingly intimate. The same currents that may be stirring Ethiopia and the Ring of Fire are passing, in miniature, through the rock beneath your shoes. None of this is meant to romanticize danger. Ash, lava, and shaking are real hazards. People who live near volcanoes and faults carry a heavier share of this season than those who do not. Yet even they, especially they, have long traditions of listening to the ground without dissolving into fear. Stories about unusual animal behavior, strange skies, and subtle changes in the taste of well water are not just folklore. They are forms of attention, ways of staying in relationship with a living crust. In a world that measures almost everything, it can feel strange to honor such subjective signals. We are trained to trust instruments and distrust feelings. In the case of 3i Atlas and the Earth's pulse, the most useful stance may sit somewhere in between. Let the data speak where it is clear. Let your body speak where it knows something quietly. Hold both, side by side, without forcing them into tidy conclusions. It may be that when December has passed, the season of this visitor will fold back into the larger pattern of Earth's restless history. The volcanic spikes will ease, the hum in the oceans will fade, and charts will show that the crust has settled into a new, slightly different balance. In that outcome, the most important changes will not be the lines on graphs, but the way some of us learned, for the first time, to feel the planet as a circuit we were already part of. And if the adjustments go deeper, if this really is the opening of a longer geological reset, like the one 12,000 years ago, your posture still matters. You cannot steer plates or plumes, but you can choose to inhabit this time with a kind of gentle clarity. You can remember that whatever 3i Atlas is, whatever currents it drags through the solar field, you are experiencing them filtered through the immense resilience of a world that has carried oceans and continents through far stranger encounters. So when you think of the close approach, try not to imagine it only as a date circled on a calendar or a speck on a diagram. Imagine it as a slow inhale and exhale between sky and stone. The magnetic fields will twist a little more. The sun may flicker. Currents will thread through the crust, nudge faults, warm a few pockets of magma by a fraction. Somewhere, a volcano may wake. Somewhere else, nothing at all will happen, and that quiet will be just as much part of the story. What you can do in those moments is simple. Place a hand on a wall or on the floor beside your bed and let yourself notice that you are touching the same planet whose pulse you have been hearing about. Feel your own heartbeat and understand that it, too, is an electrical rhythm, tiny compared to the currents driven by 3i Atlas, but made of the same basic language. Two oscillators, one small and warm, one vast and mineral, sharing a span of time. As this journey draws to a close, you do not need to hold on to every detail. You do not need to remember the names of plumes, the classifications of flares, or the precise distances of closest approach. What can stay with you is softer. The knowledge that Earth is thin-skinned and sensitive. The sense that the planet reacts, sometimes violently, not only to what rises from within, but also to what moves in the sky. And the quiet comfort that even now, under new kinds of stress, it is still finding ways to redistribute its load rather than shatter. Let your awareness widen one last time. Picture the Ethiopian volcano, the arcs of the Ring of Fire, the dark ocean basins humming, the faint veils in the upper air, and far beyond them, the small, bright point of 3i Atlas gliding along its path. Then narrow your focus back down to wherever you are. The chair, the mattress, the floor, the single local patch of crust that is holding you tonight. In a few minutes, the images will fade into the softer colors of dream. The interstellar hull will continue on its way whether you watch it or not. The Earth will keep adjusting, using the tools it has always had. For now, it is enough to know that you are resting on a living, reactive shell that has carried life through shocks and resets and long calms beyond counting. Let your breath follow that larger pulse. Slow, then slower. Let the thought of distant generators and magnetic fields drift to the edge of your mind. Feel instead the heavy, patient presence of the planet under you, and trust that whatever passes near, whatever currents rise and fall, you are lying on a world that has spent billions of years learning how to survive the sky. Sleep, if you wish, not by looking up for danger, but by feeling, very quietly, the steady, changing ground that has already noticed 3i Atlas and is answering in its own deep time.